So I showed you a couple days ago, we have this wire. The wire is not ferromagnetic, so it does not make a good magnet. It cannot be magnetized with just bringing a bar magnet close. It's not attracted to it. Yet, if I make current flow through the wire, being temperamental today. I'm not sure why it's not cooperating. So if we flow current through the wire, we now have a repulsive force that's pushing the wire away. And that's because of the interaction. The wire itself, having current flowing through it, it's now creating its own magnetic field. And that magnetic field is interacting with the external one of this magnet. So we're getting a force. So a wire carrying current, because it creates its own magnetic field, it may feel a force due to an external magnetic force that it lies in. Now a single charge also creates a magnetic field, so an individual little charge moving. I don't have a way to show you one single charge that's moving, but I do have this. So I have pieces of aluminum here. Aluminum is not a ferromagnetic material, so it does not become magnetized. If I bring a bar magnet close by, I cannot attract it. So I'm going to just make a little pendulum out of this. I'm going to make it so it can swing through this magnet. So basically, this is kind of a stretch of the imagination. This is a conductor, which means electrons easily flow in the conductor. Okay. If I move it, it is now a bunch of moving charges. Right? Okay. I know it's kind of a stretch there. If I take my little pitchfork shaped one and I swing it through here, it eventually slows down and comes to rest, which it would do normally, but it's doing so faster than it did without the magnet there. So as these charges move through the magnetic field, they're creating their own individual magnetic fields, which are interacting with that external one, and they're experiencing forces. Now, the reason why we don't get anything terribly dramatic, for example, if I change it, here it looks kind of like a comb, here it's now a spatula. It has that strip along the back. Same material, but now, when I swing it through there, we get a much greater reaction. It stops very quickly. And it stops very quickly. In both cases, the charges end up feeling a force. The difference is the charges in here have more pathways to take. And as they have more pathways to take, they're going to create a bigger field, which results in a larger force. So this guy, totally solid, make sure he doesn't hit. He stops immediately. He doesn't even swing through at all. And that's because there's unlimited space for the charges to move around in. We get in there, actually, an induced voltage. What happens is it actually ends up separating the charges and we get an induced voltage in there. We call it the Hall voltage. We'll talk about that in just a minute. So, kind of a stretch, but they are moving charges. And they feel a force. So the equation. Force equation looks like this for a single charge moving through an external magnetic field. So B here is the magnetic field external to the charge. It is not the field that the charge itself is producing. This is the external one created by something else, whether it be a permanent magnet or something else. That's the magnetic field that the charge is moving through. V is its velocity. The charge has to be moving in order to create its own little magnetic field. It's not going to experience a magnetic force unless it's moving. Q is the charge itself, how much charge is on the, whether it be a proton or electron or a nucleus or something like that. It is a cross-product equation, meaning the velocity and the magnetic field must be perpendicular to each other, or it's only multiplying the components that are perpendicular to each other. The force itself is perpendicular to either one of these. So for example, let's say we have a proton and it's moving upwards. And it's in a region where the magnetic field, due to something, I don't really care what is creating the field. Let's say the magnetic field everywhere in here is into the board. So whatever is creating this magnetic field is into the board. Now, that's not the field due to the charge itself. The charge is creating its own magnetic field. But that magnetic field I've drawn is due to something entirely different. So the velocity is perpendicular to the magnetic field. So the magnitude of the force would simply be QVB. If it's not perpendicular to the force, if the velocity is not perfectly perpendicular, then you just have to find the component of the velocity that is perpendicular. Right-hand rule. We have a right-hand rule that works for all cross-product equations. Doesn't matter what they are. You put your index finger in the direction of the first vector. The second vector needs to come out of your palm. And your thumb is the direction of the resultant vector. So the first vector is the velocity, so I put my index finger in the direction of the velocity. The second vector in the equation is a magnetic field. The magnetic field points into the board. I need to keep my index finger pointing up, so I twist my wrist until my palm can point into the board. So something out of my palm can point into the board. My thumb is the result. So the force on this proton is to your left. So this charge starts doing that, starts curving. But now its velocity is in a new direction. If the velocity is in a new direction, the magnetic field's in the same direction, the force is going to be in a new direction as well. If my velocity is now that way, I need out of my palm to point into the board, so I twist my wrist so it can point in. My thumb now is pointed down. The force on this charge now is downwards. So it starts curving this way. But now its velocity is downwards. The magnetic field's into the board. So velocity down, magnetic field into the board. The force is to the right. The net result, the magnetic force on a charge is a centripetal force. It causes the charge to move in a circle. We can relate this, Newton's second law, if the magnetic force is the only one acting on your charge, we can say that force is equal to ma, Newton's second law. But the centripetal acceleration is v squared over r. So we get a direct relationship between speed, magnetic field, and then r. For example, the radius of the circle our charge will move in is equal to mv over qb. The faster it's going, the bigger the radius will move through. The stronger the field, the smaller the radius will be. So, force on individual charges moving through the field will result in the charge moving in a circle. What if it was a negative charge instead of positive? Go the other way. V cross B is what we've looked at. Well, if you multiply that by a negative Q, you just get the opposite direction. So if you had a negative charge coming in here, it would circle the other way. They actually use magnetic fields in particle accelerators, keep them going in a circle. And they use the potential, electric potential, to speed them up so they go faster and faster and faster. And eventually collide. Similarly, if we have a wire that's carrying current, it will also experience a force as long as the current is perpendicular to the field. So like here, if our velocity, if our charge had been moving into the board and the magnetic field into the board, there would not have been a magnetic force. If V and V are parallel to each other, then there's no force, at least no magnetic force. That's the whole purpose of the cross product. It's only perpendicular components that result in the force. So any parallel component of velocity will not change. With a current carrying wire, instead of writing it as Q times V, remember velocity is distance over time, we shift the time under the Q. Q over time is current. So we get current times distance, or length in this case, crossed with B. So if I have a wire carrying current, in this case I'm going to say our current is flowing to the right. Let's say it's in the same magnetic field as our last example. So this magnetic field is created by something else. That magnetic field is not the one created by the wire. Now the wire is creating a magnetic field, but a wire cannot exert a force. A long straight wire cannot exert a force on itself. So this magnetic field is external. It's something else that's creating it. The direction of L here, L represents the length of your wire. The direction of L is the direction the current is flowing. So the direction of the current must be perpendicular to the magnetic field in order to feel a force. And right hand rule again. We put our index finger in the direction of the first vector, so I. We twist our wrist until the second vector points out of our palm. Well, our magnetic field's into the board again. So my thumb is pointing upwards. So the force on this wire in this magnetic field would be upwards. Common example would be, say, yesterday we looked at two parallel wires that were both carrying current. We'll call them I1 and I2. They were some distance apart. Both wires are creating magnetic fields. That means wire 1 is placed in a region where there is an external magnetic field. What's creating the external magnetic field?
Wire 2.
Wire 2, exactly. So wire 2 is creating a magnetic field over here. The direction of wire 2's magnetic field is out of the board at that location. So B from wire 2 is created here. It depends upon the current in wire 2 and how far away we are. Since wire 1 is in this external field, it's going to feel a force. We can easily find the direction if we put our index finger in the direction of the first vector, which is the direction the current is flowing. We let the second vector, the magnetic field, come out of our palm. Our thumb is the result. So the force on this wire, due to this magnetic field, is to the right. The force magnitude is easy to find. We're trying to find the force on wire 1, so we need I1. We would need to know how long it is, and then we need to multiply by the magnetic field, the external one that wire 1 is in. Well, we already said wire 2's magnetic field is the one creating it. So our force on wire 1 is equal to mu naught L I1 I2 over 2 pi d. But wire 2 is in an external magnetic field as well. Wire 2 is in the magnetic field that wire 1 is creating. Wire 1's magnetic field over on this side, my fingers would be pointing in, so the magnetic field from wire 1 would be going into the board here. So B from 1 would be mu naught I1 over 2 pi d. Direction of the force, if we do the right hand rule, put my fingers in the direction of the current. I need to twist my wrist so that the magnetic field vector points out of my palm. So I twist my wrist that way. My thumb points to the left. The force on this wire is to the left. Magnitude of the force, using our equation, the I in our equation up here will be I2, because that's the wire feeling the force. L is however long it is, times the magnetic field, the external one that the wire is in. So the mu naught I1 over 2 pi d. Notice we get the same answer either way, which should make sense. Newton's third law, for every action there's an equal and opposite reaction. Whatever wire 1 is doing to wire 2 is doing back. So if wire 2 is attracting wire 1, then wire 1 needs to be attracting wire 2. So those two wires will attract each other. And if they were not rigidly fixed, they would physically come together. So any two wires carrying current in the same direction will attract each other. What if one of these was flowing the other way? So one was up and one was down. That would change the direction of this magnetic field, which would then make the force in the opposite direction. So if our wires are flowing current in opposite directions, they'll repel each other. So whether you want it or not, any wire in a magnetic field is going to feel a force. As long as the current flowing through that wire is perpendicular to the external magnetic field that it lies in.
So
Questions?
if you were to turn I2 upside down, would they attract?
If I2 was put upside down, they would repel. Because if this current was flowing downwards, that would change our magnetic field over here to be into the board.
Oh, they're currently attracting down.
Yes.
Okay.
So they're attracting when the currents are going the same direction. If we flip the direction of one of these currents, that changes the direction of this magnetic field. So IL crossed with B gives you a vector that's that way. So they would repel each other. One other equation that's related. We said, for example, for a bar magnet, inside the magnet, we call that the magnetic dipole moment. Our book uses a mu. Please don't confuse that with mu naught. Mu is the magnetic dipole moment inside the magnet. Now certainly it has a magnetic field outside as well. If we have a bar magnet in an external magnetic field, say our magnetic field was off at an angle like this. So some sort of external field. An example of this would be a compass needle in the Earth's magnetic field. What's going to happen? It's going to rotate. Right. Remember magnetic field lines, whatever's creating this external field, there's some sort of north type polarity down here and some sort of south. So the north pole of my bar magnet's going to want to go towards the south, but the south pole of my bar magnets want to come towards the north. So overall, the net force is 0. The magnet itself is not physically going to move, but it will spin. So it experiences a torque. It'll twist. As you said, it'll twist until the magnet lines up that way. The torque is equal to the magnetic dipole moment crossed with the magnetic field. And again, B there is the external magnetic field, the one created by whatever this magnetic field is created by. So these are our main equations that describe forces, the motions in the field. So we have force on a moving charge, the force on the current carrying wire, and the torque. Remember, torque is a twist. The torque on, say, a bar magnet, something that has a magnetic dipole moment.
How can you do the field lines in the external magnetic field from north to south, and then inside the magnet from south to north?
That's how the
Is that just
magnetic
how it
field lines
goes?
go.
Okay.
Outside
Why?
any magnet, it's always north to south.
Uh-huh.
Inside, they continue on south to north.
That's just the way it is? Okay.
Magnetic field lines don't start anywhere and don't end anywhere. They're continuous. They have to make complete loops. So if they're going north to south outside the magnet,
Then they have to be going in the opposite direction.
right.
Okay, gotcha.